Hello, it's Dumplet here. Here's an item on number theory. Let x and y be non-negative integers greater than or equal to 0, such that the following equation holds. xy plus 2 quantity squared equals x squared plus y squared. So find all possible ordered pairs x comma y. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now, whenever we're given with an equation where the variables involved are integers, it would be very nice for us to be able to factor, because since we're working with integers, if we can make the right hand side of an equation become a constant, and then the other side of the equation we can factor stuff, we can use the concept of just assigning positive divisors of the constant term on the right side. So we can try to implement this. So let's start by expanding this first. So xy plus 2 quantity squared. Now, well, this simplifies to this one. So xy plus 2 quantity squared equals x squared y squared plus 4xy plus 4. Now we can manipulate this in a very creative way. Now note that this 2xy this 4xy over here can be written as 2xy plus 2xy. And then this 4 over here, let's write this as 1. So the 4 over here, let's write as 1 plus 3. Now, I will have here x squared y squared, 2xy, and 1, and that's a perfect square, so I can write this as xy plus 1 quantity squared. Now, the 2xy, let me put it on the other side, and then the plus 3, I'll just write plus 3 for now, so plus 3. This equals, so the right-hand side, we can implement this, we can incorporate this with the 2xy, because it's going to be x squared minus 2xy, and then plus y squared, and we know that this is factorable, so we can factor this into x minus y quantity squared. Now we have square 1 here and then square 2 here, so we can rearrange the terms. We can get something like this, and let's put the 3 on the other side. So we're going to end up with some equation like xy plus 1 quantity squared, then we're going to subtract x minus y quantity squared, and this equals negative 3. And this is nice because we have a constant here at the right hand side, and we can factor this since this is a difference of two squares. So we can factor the left hand side of the expression using the difference of two squares. So take note that a squared minus b squared can be factored into a minus b times a plus b. So we can do the following. Now we have, after you simplify, you're going to get this equation here. Now we can assume the following for now. So without loss of generality, let x be greater than or equal to y. Now, why is this the case? Let's go back to the given. Now, it's obvious for us to see that if x comma y works, then we will have another solution, y comma x. So we can interchange x and y. So that's why we can say that without loss of generality, let's just assume for now that x is greater than or equal to y. Now, sometimes it's helpful, sometimes it's not, but generally speaking, if you have a symmetric equation, then you can try to let one be greater than the other, and you can implement some other things that you might not be able to if you don't assume instead. Now, after we have the factored equation, we have negative 3 on the right. So we know that the factors, this and that, should be factors of negative 3. Now, with the assumption that x is greater than or equal to y, take note of the two factors. It's xy minus 1, and then we subtract x minus y, which is a non-negative value via our assumption, since x is greater than or equal to y. And then we have the other one, xy minus 1, and then we're adding a non-negative integer, since x is greater than or equal to y, as per the assumption. So we can say that this blue expression here, it's going to be greater than or equal to this green expression here. And we can assign the following factors as so. So two numbers multiplied to negative 3, so it must be negative 1 and 3, so negative 1 and 3, that's case 1, or negative 3 and 1, that's case 2. So since we've arrived at the conclusion that this term is greater than this term, we can assign 3 here and then negative 1 here, and then 1 here, and then negative 3 here. So that's a very nice implementation of what we can do. Now, instead of just letting each of these expressions equal its respective factor, we can try to be creative about this and take note that if I take the sum of these two, if I take the sum of the two factors, this one and this one, note that I'll be getting simply 2xy minus 2. Now the x minus y and the x plus y here, x minus y and the x minus y here cancel. So I'll get 2xy minus 2. So case 1, it's just actually 2xy minus 2 will equals 2. So because negative 1 plus 3 equals 2. And then for the second case, negative 3 plus 1 equals negative 2. So we have two cases. So this 2xy minus 2, I can, case 1 will give me this, and then case 2 will give me this. Now, we can do the following. Because we know that x and y are non-negative integers, from the first equation, what can we get? We can get that 2xy is 0. So we're going to have x equals 0 or y equals 0. Now, since we know that, right, we are going to write xy equals 0. So since we know that x is greater or equal to y, if x equals 0, then y must equal 0. But, well, if you substitute x and y here, it's not going to work. So we can easily check that it's not going to work. So from the conclusion, from this, we're going to get that y equals 0 instead. Now you can do this as an exercise. If y equals 0, substituting y in this blue equation above, you're going to get the solution that x equals 2. So from case 1, we're going to get the solution 2, 0. Now for equation 2, you can see the following. So 2xy equals 4. So we're going to get that xy equals 2. Now take note, x and y are non-negative integers. So, well, the factors of 2 are only 2 and 1. So we must have the following. We must have the ordered pair 2, 1 to satisfy. However, if you try 2, 1 in this equation above, you'll find that this is not the case, and 2, 1 will not satisfy this equation. So from this, we can conclude that only one works. And it seems here that we only have one solution, but take note, we have the without loss of generality assumption that x is greater or equal to y, and then that's due to the fact that if we know that x, y is going to work, then y, x is going to work. So don't forget to include the other solution, which is going to be 0, 2. So to finally answer this question, there are two ordered pairs, 2, 0 and 0, 2. And these are the solutions. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!